Hello, this is the first lecture on human performance field investigation. All right, so we'll start with just kind of some definitional, what is human performance? So there's a lot of different definitions out there. In general, in our application, we're going to define it as how people function within work or organizational systems. So this will involve looking at human fallibility, different environments, systems, designs, and organizations. It also can be a big focus for processes and other laws, different things that govern how we conduct ourselves in different ways. So, what is different about human performance investigation in the sense of relative to, let's say, just general accident or event investigation? It really comes down to just the subject of the investigation, right? In a human performance investigation, we are looking at humans, um, and humans have specific limitations or variabilities that physical realities don't. So humans and perceptions are not always concrete or measurable. There tends to be significant variety across different people, different perspectives, especially, how memory is encoded and things that we'll get into. And there's just some unreliable psychological realities, some things that are inherent about being a human and having thoughts that make doing this type of work a little bit more difficult. It can sometimes feel like we're doing something as unorganized as Calvin Ball. So next we're going to go into kind of just some foundational psychological baselines of how some of our cognitive systems function. The big focus for this course is going to be that you understand what drives human performance, what obstacles are presented just naturally, and then eventually how we can get to the bottom of those and potentially correct or prevent them in the future. So looking at psychology, it's the study of behavior in the mind. So I like to start with this as a little bit more of a historical slide, really, but psychology has largely been defined over the last 100 years along two lines. For the first half, it was very behaviorist. We focused on whatever the argument was, whatever's going on in the brain is what comes out in behavior, and that's all we can access or interact with. So we saw a lot of stimulus response type studies and focusing on behavior modifications in those aspects. Since about the 60s, 70s, there was a pivot towards cognitivism, so a more cognitive approach which acknowledges that there are things going on inside the brain that don't manifest behaviorally but that can still be studied. And so this is where we would look at what's within the box and what can we glean from certain research about that, so that we can maybe help solve problems before we ever even get to behavior. And I always look at this as a breakdown between prevention and response. And not that one is better than the other per se, but behaviorism is post hoc by definition, right? A behavior has to manifest for us to interact with it or do anything with it. Cognitivism is the first step to a prevention approach. So when we look at like investigations, corrective actions, regulations, they're all post hoc. They're typically in response to something, where design tends to be the preventative piece. So if we look at just a human performance event, there will be some aspects of design or the task construction that may have played a part in the eventual result, and then there are the responses, the what happened after the event. So those are each distinct components that we'll be looking at. So we're going to step through sensation, then perception, and end up in cognition. And this is kind of a good way of understanding the hierarchy of our kind of just the neural networks that we deal with. So looking at sensation, sensation is our five senses. It is the physiological capacity that allows us to collect environmental data that then can be perceived. It gets passed to our perception. It's also can be considered transduction of energy through our sensory organs. So the energy that our eyes transduce is light energy. Our hearing transduces audio waves and those kind of things. So that is what we mean when we mean sensation, is just the rawest form of you collect it, your body is collecting data and passing it upstream. When we look at perception, perception is the organization, identification, and interpretation of that sensory information in order to represent or understand the world around us. So instead of just, oh, there was a huge, like the sensation, if you look out at your front lawn, your sensation says, look at this big smear of green. And then it hands it up, and your perception looks at that within the broader context, maybe looks at different shapes and all of that to try to ascribe some meaning to that sensory information. And that's where we get to perception. So that's where you would see a lawn. You don't just see a big smear of green, you see a distinct thing. And that's how sensation would hand off to perception. And then finally we get into cognition. So this is our looking at our ability to think. So this is the next step, right? We get sensory information, it goes through our perceptual processes, and then it gets handed up to our cognitive processes where we can acquire understanding, think, experience, and reflect primarily. And cognition, I like the ability to think is a very simple way of breaking it down. But if we want to talk about rational cognition and things, what sets us apart, right, from other animals, it would be the ability to think about thinking. So second order metacognition. So we're going to go through a few of these models, none of which are the end all be all. So when you're looking at this, be aware of that, that there are different models of human processing and human cognition, and there isn't one necessarily that's right. All of them probably get pieces right. We're still very, very early in our understanding of how we process information cognitively and understand it. So here is kind of a fundamental information processing model. That's a specific type of cognitive model that we'll look at. So it's relatively straightforward. We have environment and cues. They get handed into our senses, which then gets handed into our perception, which then goes into this working memory and cognition. This also is within this gray box, right, which is our situational awareness. And then we have a choice, an action, and then the executing of that action. And this is typically how this works, but it does prevent a linear process where cognition is not really linear per se. So a big point that we're going to look at throughout this course is that humans have limited cognitive resources. So our main resource, let's say our main unit that we spend, is our attention. So there are different arguments about this. For a long time, there was the single resource theory. So all of our cognitive resources were one big pot. They got split up as our task demands did, or presented themselves, but it all came from this one big pot. So if you hyper-focused on one thing, you could dedicate all of your attention to that thing. Then we ended up with bottleneck issues because there were certain things that people would report that represent parallel processing problems. So this would be an example of if you're reading something and then listening to text or some kind of a verbal information, those two will conflict. A lot of people have experienced that where maybe you're typing something and you type what you hear but not what you meant to type. That led us to the multiple resource models, where we look at how information along similar modalities can interfere. And so our attention seems to be more split fundamentally than the single pot of resources would make us think. You'll hear the term slip and lapse throughout this course. Those are both types of errors. We'll get into those later, but a lapse is a storage or a memory error, where a slip is typically an execution error. You meant to do the right thing, but your hand didn't work right or something like that. But fundamentally, right, the point of human performance field investigation is we know people have limited resources. So getting to the truth of a situation after the fact is a very delicate and difficult process sometimes. So here's another example of the model human processor. So this is another informational processing model that was popularized in the 80s. It makes use of a lot of computational type ideas. So sometimes you'll hear it referred to as a computational theory of cognition. But it basically breaks everything down into specific milliseconds or chunks, which are specific units that we use, and it tries to bound our cognition in some of these ways, similar to how a computer would be bound. You know, how many operations a processor can do at any one time is a known number. We can get that number. So this was another theory about what might be going on between the ears. So now we're going to, we've went into a couple theories of cognition. We'll get back into them in a little bit, but I'd like to spend some time specifically on vision and on just the way visual processing works. So what you'll run into is visual processing has such a significant role in our overall cognition, and that is because our brains are visually wired or visually biased, let's say, amongst our sense organs. So almost 50% of your brain gets involved in visual processing. 70% of all your sensory receptors are in your eyes. And one of my favorite facts about humans is it takes us less than 1/10 of a second to get what we call the gist of a visual scene. So in that short amount of time, we can understand roughly what's going on in the scene or the thing that we are viewing. Now, when we break down vision, just a little detour into visual theory a little, but maybe some anatomy. So we have rods and cones. Our cones are our foveal vision. That's our vision right in front of our pupil. And then the rods affect our peripheral vision. All of your color vision comes from your cones. Most people have 3 cones. Some have extra, and those folks can see additional colors or gradients than others can. But this is kind of just a breakdown of the difference between cones and rods and how they play together in, just looking at like slow versus fast perception as an actual neural processing unit. But to make it more concrete, if you're looking at foveal versus peripheral vision, if we look here on this very blurry, even the non-blurry things are blurry. This little area where the little lectern is here would be our foveal vision. So it's roughly 5 to 8 degrees across from the center of our pupil. Our field of view is much bigger. But then there's this green area, or not green, gray area here. And that's our blind spot. So we'll get into that a little bit more with saccades, but that's an interesting aspect that we all have. So looking at human error, which we'll get into more in the next video, but human error, because that's generally what we're looking at. When people are doing human performance field investigation, they're trying to get a sense for, did somebody make a mistake? So it's largely, and this is a long kind of circuitous definition. Don't worry about necessarily remembering it, but it's a general term to encompass all the occasions where a planned sequence fails to achieve its intended outcomes, and when those failures can be attributed to something outside of uh, just some chance agency, right? This is when we're talking about human error, it's because things didn't just show up and make you make a mistake. So it tends to be kind of outcome dependent, possibly. There's also this discussion of chance agency. What does that mean? That's some wonderfully not expository phrasing. And planned is doing a lot of heavy lifting here. I don't know about you, but most of my mental or physical activities are not always planned, in that sense of when I think about grabbing a cup off of a counter, am I planning that really? Am I deciding what angle, what height do I put my hand and those things, you know? So planned is one of those that can get a little bit sticky, but we'll get more into human error later. And why are they error prone? We talked about this when we talked about human performance, right? We have limited resources, and we'll get into this SRK, slips, lapses, and mistakes. All of this will come up in the human error taxonomy section in the next video. So can you intentionally make an error? This is one of the things I always like to bring up early in this course, is we're looking at how we will investigate human performance in the event of an accident or some negative outcome. Can you do an error intentionally? Which sounds kind of strange. Like, of course not. It's a mistake. Mistakes can't be intentional, right? That's like fundamental to what a mistake is. But it's important to break down that about what about intentionality. So if I reach to grab a cup off of the counter, I misjudged the depth and I knock it across the way. I did not intend to knock it across the way. So then why did I? What happened? What broke down in the systems of my sense organs or perception that led to that outcome? Now, this is totally exempt from what we'll call malicious compliance or sabotage, when people are actively engaging in the wrong action. That also wouldn't be an error the way we understand it. But then these last two questions are really critical to this course, really. How do we know we made an error? And how can we know why we made an error? So if we go back to the cup example, if I knock it across the room, how can I access what I did unintentionally? You know, how do I reconcile that cognitively? And we'll get into some ideas about why that is. But when we're doing human performance investigation, we're really trying to get at, how did this person do something that had a result they didn't intend? And how can they know that they did that in the moment? Because if they intended to do something else, wouldn't they have done something else? And so that's kind of the inherent tension of what we're doing here, and why it's important to really be conscientious as we go into here. A lot of times people want there to be a human error, but in a lot of instances there just isn't one. It could be that that person was set up to fail, or the design was inadequate, or different things like that. So we always have to keep that in mind. So if we go back to the whole behaviorist cognitivist thing, right? Behaviorists, that's what we're doing here. We're going to come in and investigate after the fact. We're going to investigate the behavior and try to get a sense for what that is. The cognitive side, right? This is where we get into design. So some amount of human error is always going to occur. That is a given. Everybody makes mistakes every day. You can't get away from it. It is an aspect of being human. So if we look at two areas of this, human factors and human reliability, human factors tends to focus on the design. So how do we improve the design of this system, task, organization, etc., to complement the capabilities of the human? How do we set up the human for as much success as possible. They can't get 100%, but we can get them as close as possible. Historically, we look at this from a usability and efficiency emphasis sometimes. Human reliability, this gets us back into the post hoc area. So we won't spend a ton of time on it in this course, but there is an entire field of human reliability analysis that focuses on trying to model tasks to try to understand the probability of an error occurring and what that human error risk does to the overall system risk. And the emphasis when we look at human reliability typically is on safety. We want to catch the things that maybe design missed and try to attack those before they become an event. So in our modern ubiquitous computing world, I like to always include something like this about technology, especially now. Lately, we've seen a lot of push for more automation, more AI, different things like that in our systems. And a lot of these have a lot of potential to help a lot of folks execute many tasks. But the one thing I always like to note, and this comic captures it perfectly, is humans are unpredictable. They fail in ever-changing weird ways that designers and developers would never expect when they created a system, or when somebody created a task for this employee. Nobody would have guessed in a million years that they would have made this mistake, but they will. So while the technology can get us closer to the goal, we'll always just have, everybody will have a Dave that breaks things in a way that doesn't totally make sense and that nobody could predict. But it's still something we need to try our best to capture because something was broken. And so that's one of those big things I always like to stress, right? Is that we can't proceduralize or train or design systems to totally prevent error. People will do some weird stuff, and we have to be open to that. So we're getting into the human error stuff next. So one thing I like to point out, so human error and risk. So this is a relatively recent, review of incidents where human error was deemed a root cause. So I like to clarify this. Percent of incidents where human error was a root cause, well, that describes reality. It's more was determined to be a root cause by whoever investigated it. And these are along different industries. But one thing I would like to point out, well, two, I should say. One, you'll see these trends every so often about human performance and human error. And it's always like, oh, humans are the reason everything fails. And it doesn't take into consideration that typically we're comparing across a time scale. And in that time, engineering, computer science, systems develop and perfect at a far faster rate. They evolve much quicker than humans do. So the human today does not have a ton different. They don't have a lot that is different about them to a human performing a task in 1915. Humans haven't changed that much in that time. Meanwhile, look at how dramatic the technology and engineering has changed. So that's an aspect to be aware of, is that of the things where an event did happen, yeah, the machines don't fail as often, for sure. But I would also like to point out a second thing, and we'll get through this through all the lectures, but I always look at it as human error isn't a root cause. Like, just fundamentally, human error can't be a root cause. Because again, if the system is designed for maximum capability, even if a person makes a mistake, there will be an opportunity for recovery. There will be an opportunity to fix whatever happened. And that's a big thing that we just don't always recognize. So I will encourage you to always try to find a root cause that isn't human. And we'll talk about how to do that and the different methods and tools that we use. This point I just made. Can human error ever be a root cause? This is a great design issue. I do not remember. Something must have changed with my PowerPoint because this used to be a different color, not black. Because look right here at how hard this is to read. That's a great design failure. But there's this saying in human factors that we have, which is there's no human error, just bad design. So I love this image. It's a bike right here. But then you're telling people to run into these poles. And we might think, well, yeah, but you see the pole, you get around them. Okay, well, which is it? Do I listen to your marking or do I listen to my eyes? And if it's both, okay, but why isn't this marking better? So we look at that kind of background and see if somebody rode their bike, they saw this marking and they kept going and they hit this, did they make a mistake? And how do we argue that, especially when we look at it from corrective actions? So we'll get there in the future about, okay, you identified a cause, now you have to fix it. And what does that look like? You can't make people stop being people. So what are we going to do with that? In this instance, it'd be move the marking so people don't run into these. And we've talked about this a lot, to err is human. Every human action is subject to imperfections. But also, and things I'd like to know, is the same qualities that make human actions error prone are also the things that give us tremendous resilience. So humans spontaneously recover from the vast majority of errors. This could be saying the wrong word and immediately correcting yourself. This could be, oh, I accidentally deleted this thing, but I can undo it. Those kind of aspects. Like we tend to be fairly reliable in that sense. And most human errors are not single point failures. It's not that everything else would have worked if just that pesky human would have done their role. That's not totally what happens in reality, though. Humans are taking actions as a part of a broader system within technology, organizations that have their own economic or social or political pressures and different things. So human performance is typically tied up in all of these things. And I'll leave this up for a bit. If you're interested, pause it. It is kind of a bit of an unwieldy definition. But one of the things that I like about it is what it's arguing here is, and I'll just pull it out a little bit here so it's a little bit clearer. Man has a remarkable ability to integrate the responses of a vast number of receptive elements, those are our sensations, according to exceedingly complex nonlinear rules. Yet, once all of that is done, so once we're past the sensation process and maybe even some perception, and it gets handed up through to cognition and memory and all of these things, once we do all of that, there's very little evidence that we can juggle and recombine all of those judgments and properties and objects with anything like the speed and accuracy of the first step. So it's one of those great paradoxes of human cognition of we're really, really good at pattern matching and recognizing specific elements in our world and how those interact and that, but then after the fact, trying to reorganize our perceptions or our memories, we're really not able to do that. So it's one of those interesting, wacky things about cognition. And then we look at human nature. So in this book, Design of Everyday Things, one of the most prominent design books of all time. So today we insist that people perform abnormally to adapt themselves to the peculiar demands of machines, which includes always giving precise, accurate information. We're really bad at this. At every level, humans are not great at precise, accurate information or precise, accurate actions repetitively. We're not very good with that typically. And so we have different cognitive components that they don't work properly. So we have changing memory states, vigilance, our sensory perception can be unreliable, Sometimes we have, you have folks that may be colorblind or have hearing loss, and so they're limited in some of those angles. So how does that manifest in their performance and in the supports that we would give them to perform adequately? And I love this quote this is from Fargo season 1, where the question's asked here of Billy Bob Thornton's character of how he can shift into a completely different persona. And his answer to this police officer is, did you know the human eye can see more shades of green than any other color? And he says, when you know why that is, you'll know the answer to your other question. And that's an interesting one there. And you may not have been aware of that the human eye sees more shades of green than any other color. That's because of predators. That's because we needed to be able to see through the jungles and the grass to spot the tiger or the bear. We needed to understand the gradients of green and all of that, those aspects. In the modern world, we don't think about that as much, but that is a reality of human nature. So it's a reminder that we can't get away easily from our kind of biological, physiological underpinnings. All right, human error will be the next video. Hope this was entertaining and enlightening. Thanks.